Let's talk a little bit more about our immediates, or constants. Remember, these immediates are called immediates because they're immediately available from an instruction, right? They're encoded in the instruction itself. We don't have to go to a register or to memory to get the operand. It's immediately available in the instruction. This immediate for load word and store word is a 12-bit 2's complement number, and also for add immediate. And here's an example, our add immediate S0, S04 for performing A equals A plus 4. We can also do the same for negative numbers, right? This could be B equals A, S0 minus 12. So we have a negative, could be a negative number or a positive number for our immediate values because it's a signed or 2's complement number. So what about subtract immediate? Do we need that instruction? No, we don't, right? We can do that operation already, right, with the add immediate. Just make the immediate a negative value. So subtract immediate, not necessary in our instruction set. And remember, smaller is faster. The fewer instructions I have to process or handle, that the processor has to handle, the faster it can be. So here's a figure showing our immediate encoding. So here's our 32-bit immediate that we're going to end up with. And our I and S type instructions encode bits 11 to 0 of that immediate, and then that immediate is sign extended, so bit 11 is replicated in the higher bits. For B type instructions, it encodes bits 11 to 1 and bit 12, and then is sign extended, so the upper bits contain bit 12, and that lowest bit will be populated with a 0 by the processor. U-type instructions encode the upper 20 bits of the immediate 31 to 12, and then the processor will place zeros in the lower 12 bits to create that 32-bit immediate. And for J-type instructions, it encodes bits, 11 to 1 and bits 20 to 12, so bits 20 to 1, and then is sign extended, so bit 20 of the immediate is replicated in the higher bits, and the lowest bit, the least significant bit, is populated with a 0. And we've written it this way to emphasize the kind of regularity across the immediates. So immediates, bits 11 to 1, all of the formats except U-type encode those bits. For U and J-type, they both encode bits 20 to 12, and U-type encodes, on its own, those higher bits 31 to 21. Now let's look at the encoding in the instruction. And so that bit swizzling that went on with, especially with the B-type and the J-type instructions, was done to keep the bits in the same location, or the same bit location in the instruction when possible. So for example, the most significant bit here, when it's encoded, is the sign bit of that number. So J-type instructions, bit 20 is the sign bit. For B-type, it's 12, and S and I-type, it's bit 11 is the sign bit, or the most significant bit. And so that's always in the most significant bit of the instruction when sign extension is needed. This is also the most significant bit, but no sign extension will happen. But that most significant bit here is in the most significant bit of the instruction, so that's consistency there. And then we can see when bits 10 through 5 are encoded, they're encoded in the same bit field of the instruction, bits 30 through 25. And similarly for bits 19 through 12 of the instruction, when they're present, so they're only present in U and J type instructions. And then there's some consistency here. Bits 4 to 1 in S and B type are in the same location in the instruction. Bits 11 to 8, so the opcode of these is not shown. Bits 6 to 0, the lowest 7 bits of the instruction, is not shown here because that's for, that's the same for all of them. And then for our I and R type instructions, bits 4 to 0 are in the same location. And again, R type instructions, this is usually RS2, but remember the one time that we encode an immediate in the R type instruction is for shift instructions with an immediate shift amount. And so that's an unsigned shift amount, and that's encoded in the RS2 field.